Hello, my name is Samuel Chang and this is my lab for Circuits and Capacitors. The main goal of lab 4, Circuits and Capacitors, is to, number 1, view and predict the behaviors of circuits containing resistors in series and in parallel. 2 is to use multimeters to measure values such as conventional current and potential differences in the circuit. And lastly, to examine and understand the behavior of ohmic resistors and capacitors. In order to accomplish those goals with a deep understanding of its results and data, it's important to know the following key principles and concepts. Number 1, the first of which is the conservation of energy, specifically for circuits as stated by Kirchhoff's loop rule, that within a loop, the sum of all the potential differences is equal to 0, and that neither charge or energy is created nor destroyed. And lastly, that because charge is conserved and the entire system is in steady state, current is conserved, and the current will not change over time. For the first part of Lab 4, we were to create a circuit similar to the one displayed here on the left, using the simulator provided. So I created this circuit board on the right. As seen in the circuit, current 1 and current 2 are the same, as this is a steady state system of a single loop. When reversed, the reading should be the same value, but negative. However, the simulator did not read so. When you replace one of the ammeters with the voltmeter, you get a voltmeter reading of 3 volts. Consequently, the second ammeter reads 0. This is because a voltmeter has a very high resistance, and so current effectively does not run through the system. When measuring voltage around the circuit using the positive lead forward going clockwise, you get the following results. Between B and A, where the batteries are, you get 3 volts. At the 47 ohm resistor, you get negative 2.041 volts, and at the 100 ohm resistor, you get negative 0.959 volts. This brings the sum of all the potential differences in the circuit to be 0, as we predicted from Kirchhoff's loop rule. After plotting the potential difference versus position graph, we can see how the potential difference changes throughout the circuit. Roughly speaking, between A and B where the batteries are, there's a potential difference of 3 volts. At resistor CD of 47 ohms, it drops slightly. Then through resistor EF of 100 ohms, it drops to 0. Wherever there are straight lines or lines of slope 0, it indicates a potential difference of 0, which means there is no resistance. When you place an ammeter in parallel to the 100 ohm resistor, the overall current increases to 0.06. This is due to the fact that by putting the ammeter in parallel to the resistor, we are shorting the resistor. In other words, the electrons would much rather run through an area of least resistance, therefore completely ignoring the route of the 100 ohm resistor. Using voltage divided by current, values which were gathered from earlier, we can see that the values we calculate agree with the settings we have set to the resistors, as well as that there is no resistance in the wire and ammeter. In the second part of the lab, we were to simulate an RC circuit using a 10 and 20 ohm light bulb, a 200 millifarad capacitor, and a 9 volt battery. In this first part, we observed the behaviors of circuits when charging and discharging the capacitor. When charging, we notice that the light bulb brightens, then dims over time. When discharging, the same thing happens. The bulb brightens again and then dims over time. The current direction when charging is counterclockwise, but when it's discharging, the current is clockwise. And it takes around 20 seconds to charge and discharge the 10 ohm bulb, and 40 seconds to charge and discharge the 20 ohm bulb. In the second part, I had graphed the natural log of delta V divided by delta V initial by the time passed in order to find the RC constant. And after solving for RC, I got 6 seconds, which matched with the RC constant of the simulator.